Hi everybody, I hope you're doing well. This video is the video that the content at least is what I wanted to show you during the live session that we were unable to do today. So we tried with Drew to start the session with on the community platform of CLN, but it didn't work today. So anyway, I will record that video as if it was live, meaning that if I make a mistake, I will continue with those mistakes and don't restart to do a clean video, but try to have something that we would have done live. So with the errors that we get in the live. So let's go. This is the part 5 of a series on Bolt 11 invoice implementation in Core Lightning. This is super fascinating, and we are at the point where we are going to implement the encoding from the string as we see at the top, foobar at the left, into the bake32 string on the right, ve hash until the queue at the end. So last time we've seen, so we can think about foobar. This is what we would put in the description of an invoice. So this is what we have seen last time. So we've seen how the Bolt 11 spec tell us to transform that string in that string foobar from UTF-8 encoding into that string that we see. So at the bottom, using the bake32 character set. So we can look at that rapidly. And what we are going to do basically, if you have some time, maybe you want to watch first the part 4 of that live. It's not you don't have to do it, because we are going to look rapidly what we want to achieve. But the last time we've seen why we're doing this and how it should be done. And today we are going to try to do it with the same way it is done in the code of Core Lightning, so that we will be able to understand the file which is in the directory command called bake32_util.c. So this is what we want, the tooling we are going to play, and maybe we reach a point where something works, maybe not, we'll see, but this is the game. So we start with foobar at the top, and we see these are character in UTF-8 and ASCII. We only have ASCII characters, so they are the same, and they have the representation as an integer. For instance, F is 102, O is 111. We see that the space is 32. So if I'm not wrong, this is the first non-printable character in the ASCII character set. Then we wrote them using the base 2 number. And we see that that F, which is the number 102, represented with 8 bits, is that number. Same way the O is this one. And we've seen that as we want to do a grouping into bytes of 5 bits, because 5 bits are contain can be a 32 number, and so we can match after the bake32 character set, which contains 32 characters. So we need to pass from that representation in with 8 bits into a representation with a grouping of 5 bits. So what is told, what the bake32 the Bolt 11 spec tells us is that we need at some point to add we maybe need, if the number of those bits that we summed is not divisible by 5 to pad them with zeros. So this is, we add a padding there and we see we get it there. And to create those group of those group of bytes of 5 bits, what we do is that we look at the first 5 here, we put them there, then we are left with 3 in that first group. We put them in the first part of the second bytes of 5 bits, and then we need 2 more, and we take those 2 more in the next grouping of 8 bits, which is O, and then we take 5 more. We put them here, and we go on and on and on at up to the padding at the end. And then those bytes of 5 bits are a number. Those number here have match are in bijection with the car set, the Beg32 car set, and we can go from 12 to V, 25 to E, and so on. And the 0 is the Q in Beg32, and this is how we get that string. So this is what we need to know, and this is what we are going to do to try to implement and to use the library that Core Lightning uses, specifically the Sican library written by Rusty Russell. So also the author of Core Lightning. So let's jump into it, and we see, so our goal is to start from foobar and to go to that string at the right, and we'll see how we can do that. And at some point we see what we need to do here at the top. So is a way when we have the character F, which is number 102, is to be able to get those bits individually and then to group them by 5. Let's go. So I have already prepared the Beg32 directory. In that directory we have 1 file Beg32. Maybe it's not the right name, but anyway, we're going to use that. Make files. We're going to see that, but as our the dependency, we already know the dependency we are going to use from Sican. So we see here this is from a Russell Sican. We're going to see how we can get those dependency in that repository and add it in our own directory. So this one, the only file that we care about is this one, the beg32.c. Okay, so we go there in Sican. We are in Sican, and we open a terminal in that directory that contain already cloned the Sican repository, and we do a make. So this will compile a bunch of stuff and some tools that are in the directory tools that we are using to get our dependency. And those dependencies need also a config.hash file that we are also going to copy into our repository. So we first run the make. So we have that. Let's go back to not live, but the not. And our dependency are tal and short types. Let's go back to the terminal. Okay, so we see. Don't think it takes much time. We drink a bit of water. Okay, so maybe something. So in the tools, one of the tools that we are going to use is a create secant tree. So this will, and we are going to put those dependencies in, let's go in the terminal. So we're done. We can see now in that directory that we have a config.hash file. So let's first copy that config file, so config.hash, and we copy it in our directory where we are going to work today. So we have that, and now we are going to use one of the tools, and this is create secant tree. So if we pass nothing, we have the help, and we see that we have to pass the output directory and the dependencies. The output directory is one up bake32 or directory, and we are going to put everything into the secant directory, and the dependencies are tar and short typed. So we are doing all those things. Now we may want to go here, and this bake32, this is where we work today. 3-L3 for that here, and we see, so we have the makefiles, the config.hash, and in the secant or dependencies, and that's it. Maybe we can see the makefiles. So we just compile these files, and also the secant source files that are that we get at the top, and we obtain the bake32 binary that we can run. So this is for the make files, and now we are going to look at bake32.c, but first, yes, bake32, yes, we can look at it. We include a bunch of library. I hope we are going to find a way to fill those boilerplates. And so far we just print foo. Let's go back to terminal, and we hope that make work. So we do make bake32, and we get we see we have a foo here, and so far so good. Now let's go back to that files, and what can we do? So one thing that I want to show you is how we are going, because we can jump to the terminal, run make, and then run the bake32 binary. But what I want to do is you see at the bottom of my screen, that part is called the echo area on my editor. So let's call it the echo area, and this is where we are going to see all the printed output from the main function. So what it does is just that when I press a key, this compiled that file and run that program, and we see everything that would go to the output, to the standard output in the terminal in the echo area. So let's see that maybe. Okay, so we have that, and we do that. So we see, do you see at the bottom in the echo area, we see as a foo. I will change it with a bar so that you can see. So I save, I press the key, and we see a bar at the bottom of the screen. So we will work like that during that session, and this is that. And let's remove that semicolon. We save, and now we press. If we we have a problem at the compilation, we jump to another screen, another buffer, where we see the compilation error, and we can work from there. So let's do that. So we see, we try to compile, we have a problem because we expect a semicolon, and we can jump to that file. We correct that, we save, and we press that key, and we see now it works, and we see bar in the echo area. So this is how we are going to work. So first thing that we need to do, let's go back to our note. And the first thing is to be able to get those bits. Okay, each for one number, one character, and a number like this, an ASCII character, bytes of 8 bits. We want to be able to get each one of those bits. So let's see how we can do that in C. So first things, maybe printf. We're going to see something. Let's go with the character f. So as an integer, we can look at f, this one. Okay. So as an integer, and as first as a character, and then as an integer. And maybe we add a new line here, and we see the f. So we press, and we see what we have in the echo area at the bottom. We have f, if we look at it as a character, and add a number, an integer, we have 102. Okay, how can we get the bits? So let's go back here. How can we get the bits of a number? So we can do a bit operation with an AND operation with the number 1, and if we do that, we'll be able with that number, if we do nothing to that number, we can get the last the last bit of that number, because if we do a AND, that means that AND with 1, we are going to have the number AND, it is 1 with 0. So if this is 0, we get 0. If this is 1 as the second, we get the 1. And for all the other, as the number 1 is equal to, so let me show that. So if we have the 1, we are going to have 1, 2, 3, 4, 5, 6, 7, and the last one will be a 1. And so if we do an AND between that one and that one, okay, we are going to have only the last bit. So this is how we can do to get the last bit. And then when we are able to get the last bit, what we are going to do is that we are going to shift to the right that number. So this one, we are going to shift it at the end and do the end bit operation. This one, we are going to shift it twice. So we put it at the end and we do the end operation. So let's see that. So we go back in that files, and what do I was telling? So we no longer care about that. Maybe we can directly use 102 so that we see what we are doing. 102, but this is not this one that I want to show, but yes, let's take example. Maybe it will take some time to see everything, but anyway, if two things. How if you already know how to shift in bits and get that information, maybe this videos anyway is useless for you, because you just have to read util the bake32_util.c, and you will get it directly. But if this is not the case, That means that there are many shift bitwise operation that need to be understand. So this is what I want to do today. So we take the time to see all those things. So okay, and a new line. We don't need the first one, and we're going to look at what are the numbers that we can take. So we can take as example those one. Okay, so we take 0, 1, 2, and 3, and the end operation with a 1. So we want the last bit of 0, 1, 2, and 3. Let's evaluate that, compile and run. So we see in the echo area that we have first zeros and ones and zeros and one, and this is what we expect, because when the number is odd, it ends with a 1, and when it is even, it ends with a 0. So this is what we get. 0 and 2 gives us with the end operation on 1 gives us 0, and 1 and 3 gives us 1. So this is how we do that. Now we need to look at the shift operation. So 3 maybe. Do we want another one? Okay, let's comment that, and we continue playing. Now we want the shifting operation. So the shifting operation, if let's take 4, let's take 1, 2, and 4. And now we are going to shift those operations. We need to see that 1, if we look at it that way, this is 0, 1, for instance. The other one here is 1, 0. If we use only two bits for representing them, and the other one, and 3 bits. Now, so we have those. They are done like that. Up. So we have them like this. So 1 is 0, 0, 1, 2 is 0, 1, 0, and 4 is 1, 0, 0. Now, if we shift, so the shifting operations will shift to the right the bits, is that one. So if we shift by 1, so this one here goes away, and as we have 0 there, we will get 0. This 0 goes away, and this one will be at the first position on the right, and this one will be shifted here. Okay, so let's compile and run that things. And am I doing something wrong? Why? Sorry, sir. No, this is not what I was expected. Okay, so let's see if we have to pack them. Okay, so maybe, okay, so let's say that we have to put them together to get the shifting done, and then replaced in the format string. So this is what we were expecting. And now if we shift again, let's shift by 2. Now we have to save, and we compile and run again. Okay, so that we shift by 2, that means that the one that was here from the number 2 one shift, it goes here, and then it goes away. And if we shift by 3, now we compile and we get 0. So what we can do is to we have to put together the shifting from the left to the right until the point that we get the bit that we want, and to get that last bit we use the AND operation. So let's put that together. So we comment that, and now we are going to mix that with the AND operation. So we have that, but if we do that, we are going to have only zeros. So if we shift by nothing, we will get the 1001. Okay, so we get the last thing. So let's see that. So we get 100. Perfect. How do we get the 010? Okay, to do that we shift by 1, so that we get the second column. Now we want the first one, so we shift by 2, we saved, we evaluate, and we see the echo area that we get the first column. So we shift in by 2, and so we get that one. So now if we go back to our note, we have a way to get all those bytes. So if as there are 8 bytes there is only 7 position we can shift. So to get the first one, we have to shift by 7. So we shift until that. If we want the other one, we have to shift by 6 and do the AND operation. So let's no, this is not that I wanted to do. We go back here. We comment that. We continue, and now instead of using 4, we are using 102, which is the F characters. And if we shift by nothing, what do we get? Okay, so let's shift by nothings. So I hope you're still with me. We have to do some of those stuff, because after everything seems more natural, and there is no secret, and we're not thinking what I'm doing, what I'm not doing. So I hope this is not too boring for you. But 102, we compile and evaluate, and we get 0. What do we get? We don't get this first one, but this one. Okay, and we are going now to do a loop to get those things. So size t and I equal, we start at 0. Then what do we want? We want I to be strictly inferior to 8, because we know we can shift only up to 7, and we do I++, we open that, and now instead of 0 here, we put vi, and maybe we want to do something, we want to put them all together in the same line. And let's see that. So we see in the echo area we get 1 0 1 1 0 0 1 1 0. The problem is that this number is if we look at it from left to right or right to left, this is the same. So we don't know exactly if we are doing if we are reading it in which sense we are reading it. In fact, what we are doing is that we are looking at as we shift by 0, we have the first one. We shift by 1, we have this one. We shift by 2, we have this one. But what we want is to go the other way. Better, we use the character O, so that we have a representation that is not binary representation that is not symmetric, so that we can really see the order we are doing. So now instead of 102, let's use 111. Is it 111? Yes, this is 111. So now we do that, and now we see that we get the thing by the end, and this is not what we want. So what do? Now we want them the other way. So instead of shifting by I, we shift by 7 minus I. So let's go to the note. So if we were to shift by 0, let's say 7 minus 0. So what we are going to do is to shift by 7, so we are going to have this one. Now, 7 minus 2, we get 6, and what we are going to have is this one. So, let's go back here, and instead of shifting by that number, we are going to shift by 7 minus I, and if we do that, we get those, we find the way to get all those bits for that number. And if we print the other one, which was 102, we also get it. So with that operation, sorry, so let's remove that one and keep that one. That operation gives us the bit, the highest bit of, I don't know how to say high, but if I is 0, we have the first bit from the left. So now we can take that and put it maybe in that function that we've called, so return. And this is how we are going to do. So we try some stuff, then we extract into a function. So the bit that we have here is the I. So which bits do we want? So we want the bit 0. C here, this is the character that we passed. U8 is defined in, this is what is defined in short type. So we can look at that. This is defined in SICAN, short types, and this is for unsigned int 8. So we use this one. We pass the C. And so far we don't use the C because we have the 111 hard coded here. But we can use getBit of car. We go there, and this is where we want to use that function. So we pass it as a character, but anyway, as we are not using really using it inside it, we doesn't care. But yes, we are using the bit. Which bit we want? That one. And now we can remove that part. Is it okay? No, we missed a parenthesis. So now this should work. So we get bit of car 111, and we want the bit I, and we are from the 0 to 8. Let's continue. So we compile and we run, and we see now at the bottom we get it. But as we didn't use the first argument of that function, we don't know if it works, because if we change it for 102, which is F, this should change, but it doesn't change. So we see that in the echo error at the bottom. This has not changed. So let's do that modification here. So this is no longer 111, this is C. Okay, this is almost how it is done in Core Lightning, but not exactly, because they pass directly a chain of characters, so an array of U8. They don't pass the character, but I think to see how it's working, we can do this like that. Maybe we get to the point where we implement it as it is done in Core Lightning, but I'm not sure right now. So we have the character, and now if we compile and run bake32, we see in the echo area that we have 0110, 0110. So this is what we wanted. We can go further and do this with the space. So if we go into the note, the space character is 32, okay, and 32 is represented by this bits representation. And if we compile and run, we get that at the bottom. So 001 with all those zeros. So let me just drink a little bit of water and think where we want to go. So we have those bits. And now what we want to do is let's remove all that noise. Okay, so now we consider that as a noise. Maybe we just skipped this one. We no longer want this one. So we are here. We have the function get bit of car, so we know how to get a character. And how to get each bit of a character, of a number. One moment, because I want to. I need to remember where we go now. Let's go back to a note. Okay, so what we want now, we are able to get bit by bit when we go there, and we would like. If you see those two table are the table of those numbers, okay? So we have all those number and those character in ASCII, and the same we have all those one with the number and their bijection with the bake32 character. So this is what we see. So we can play with that on the look up for those tables. So what we want now is to create those 5 bits. Okay, and we need to create those 5 bits. And okay, so let's go. 4, 4, 4. Let's stay with a number like that. For size t b equal 0. So now we want to move 5 bits. So we look at the bit of the U8 number, and each time we do we get 5s. B++, we want to do something. So if we do something like that, maybe we are going to print stuff. So I don't know if I'm doing the right thing, but anyway, this is what I told you. I really want to say how we would understand and do that. Maybe we close that. So when we here, when we've done we've looped 5 times, we first we do something like that. We have that, and we print the bits. I don't think we are going to have any trouble doing that. This is not the right answer, but let's see what do we get. So it's run too much, so something is not done wrong. It's not done the correct way. So 1 second. Maybe you can just compile. See, yeah, okay, so it should work. But for some reason, we get nothing printed. So, okay, let's go back to the terminal and see why. Okay, so there is obviously something wrong. Okay. It's because it's not E here, but this is B. So we do that, and this is not exactly what we wanted to do. Okay, so let me think. Okay, so the wrong thing that I'm doing in the first for loop is that we are incremented I by just 1, but we want to increment it by 5, and specifically we want to increment it by the number b, which is 5, when we go out of this, because we read the first we read 0, 1, 2, 3, so up to 5 of the U8, and then we don't want to put I to 1. We want it to pass to the number 5. So to follow also how it's done in this, so size I, size t, the I, b, we declare them, so we can here use the b plus equal b, so we increment by b here the I, and now we should have something okay, so one moment, so let's remove that. This is compiling, so okay, so we have some things that okay, we are almost in something. We see that we have 0, 0 and 1, 1, 1. This is normal because the I that we have in the first loop, this is the one that we use here, and this is not what we what we want to do. We want to do high plus b, because so here in that first one we go up to 8, because what we are looking at is the number 102 as a character of 8 bits. So we don't want to look up further. So this is the limit for I, this is something that we increment by b when b is 5 out of the second loop. And in that second loop, this is we can say that this is kind of the how to go now, not that one but the not. This is when we look at the number that we want to build. This is this represents the index of the bytes of 5 bits, that one. So b equals 0, this is that one, b equals 1, this is that one, b equals 2, this is that one, up to that one. And when we are done, we go back to b being 0, and we go again. So we need here to look up for I plus b. So let's see that. So now we see something interesting, which is Okay, this is almost what we want to have, but if we change that, let's see that one, 11, and we have that, but the zero padding at the end, we are not controlling it. We are not doing it the way okay, so let's yes, so we have we see that we have 10 number, and the last are zeros, and those zeros come from something that happened here, where but this is not how we want to do that. What we want to do is really to say when I plus b is inferior to the number of bits that we have for sure from the number that we are looking at, which is 102 or 111 for f or 0, we get the bit. And if we this is not the case, we want to print zeros, but not we don't want to do that with get bit of car. So I think that this happened because but anyway. But what we have to do here is to do a check. If I plus b, so maybe this is like that, I plus b is strictly inferior to 8, the number of bytes, we do that, and we don't need those one. Else let's print something else to see that we are not printing the 0, but we decide when we print 0. So let's print something like a dash. Okay, so normally now what we will get is we see at the bottom in the echo area. So when I plus b is strictly inferior at 8, remember that we are not looking at a string with a foo bar, but only we concentrate with one character. This one, 111 is 0, but it could be f, and it has only 8 bits. And what we need to do is to take the 5 first bits, make a group. Then we take the last bits that we have, which are we have 3 last bits, and we need to pad with something. And right now we pad it with a dash, but we want to pad that with a 0. Right now we are not constructing any how to say that, any number. We just are printing those things, because after the numbers that the bits that we are that we print in the standard output. So we see that those things that so far we are not constructing the number, we just are printing them, and at some point we need to see them as numbers. So we have to build the number 12, build the number 25, and this is interesting and funny, is that when we are going to do that, we are going to do the binary shift operation from the right to the left. But let's say that right now we print zeros here. If we do that, we have we compile run, and we get what we wanted for one character, and if we change it for 102, we also get it. If we pass 32, which is the space, we are going to have zeros at the end. So here we are. So now Let me take a little break. How do we continue from there? So now, okay, so what would be interesting is to do that for maybe for 2 characters. So let me think if this is that way the next steps that I want to take with you and with me. Yes, I think this is where I want to go with you now. So let's define u so a pointer to how do we call it, source, so which is going to be fo. So we have that. This compiled. We nothing happened, nothing changed because we've changed nothing nowhere. Let's remove that line, and now, okay. So we don't need that part. Okay, so we want to do that, but for two things. So how many bits do we have? 2 by 8, so this is 16. So we are going to have something here, 16. Okay, so if this is inferior at 16, where we are looking at, that means that we have bits that we can get from something. Now, the bits that we want to get is no longer 32, but it will be when we are from 0 to 8. This is f, and then 0. So let's keep that one here. And this is not 32 that we want. This is source of. So this is not I plus b, but this is, so if I'm not wrong, this is I plus b divided by 8. So if we are before 8 in our loop, that means that we still are looking at the first character, the f. So I plus b, so maybe we should do that like that. So I plus b divided by 8, so we get that, and this is going to be, we are going to have the f character, and now we need to do something with I plus b, because at some point this go further 8, and we only have 8 bits there. So to do that, we take modulo 8 of that number. So that should mean yes, so when we have the I at the beginning, its value is 0. We enter in that second loop, b is 0, I plus b will be strictly inferior to 16, so we are always in that part, and that part also will be what we want. So now we get something in the echo area which seems to be what we wanted to have. So we have some zeros at the end, and we have four element. Why 4? But 4 by 5 is 20, and this is what we wanted. When we get to the 70th element, we no longer get the bit and print zeros. So in the message, so everything that we've seen in the, maybe it's no, I will do that like that. So we go to the terminal, we do this, and this is what we get. So these are those things, those 5 bits. Let's go to live. No, not. Maybe we can put them here, and we can see that the first one is that one. Maybe I can do that like that. This second one is the second one. The first one is okay, and then we don't have it. This is normal. We stopped when we were at some point, and we've put 4 zeros of padding. But if we do that with all this, we will get all of those numbers. So it seems to be working the way we want it to work, but still. What we are doing is printing those numbers, and this is not exactly what we want to do. So let's continue. How do we that information that we are printing and that we enclose with brackets to give us some information. Now we want this to be real number. So we want we find the way to print the first 3 with the another one which is directly the padding, and now we want that to be that number. Once we have that, it's direct to do a lookup in the big32 car set and to get the V. But now how we when we get those bits, how do we get, when do we get those bits from the bytes of 8 bits? We pass them here. So the way we do that when we got the first one, we put it in the number, and then we are going to shift that number by 1. We get to the right, we get the second one, and we shift it again. And so we always update the last part of that number, and we shift by 1 to the left, and we do that 4 times. Yes, 1, 2, 3, 4. Yes, we do that 4 times, and at the last time we get that number, and it's okay. So we get those bits here, we put it at the end, and we shift to the left, and we get that, and then we continue with the other. Let's see if it's as clear as it seems to be right now. So we'll continue with two number, with F on the 0, and this is a U5. So we want a U5. Let's call it a U5 car, and put it to 0. And in fact, we keep it like that, and we are going to set it, let's say here. Okay, so we want to construct with the bits that we get. We want to construct, so we set it to 0. Okay, now here, what we do, we enter, and we are going to get the first 5 bits of F, after we are going to the last 3 bits of f and the 2 first bits of 0, but each time we are constructing a number that we construct in that place, and we are going to print that place, and then we are going to do that correctly in the sense where we are going to put those number in directly in an array, but step by step, to me, I think. So we shift it by 1, but as it is, this is a 0. We don't care, this is a 0, but as this is important after, when we are going to get that bit here, we need to do it that way. So, okay, so shift that expression is to take the number in U5 car. We shift it by 1 bit, and we assign to U5 underscore car that new value shifted. So this is what we do here. And instead of printed that number, we can still print it, but this is not what we want to do. We want that byte that is here. So we want that number, so that bits, and where do we want to put that bits? Okay, so yeah, so now we want U5 that car, and we do an OR operation. Before we've seen the AND operation. No. Sorry. I'm doing something wrong. Now, this is what we want to do, but after we will maybe clean a little bit this, because maybe we can just put that part here to make those things clearer. So this is how it is done in Core Lightning. So we are going to do it in a moment. But first, let's say just that part. This is the bit that we get from the U8 the U8 characters that we have, and the first one is F, the U8 number, as anywhere how we want to see that. So this is going to be 1 or 0, and we do a OR operation with the U5 car that we have. So that means that if we have 1, we put the 1. If we have 0, we put 0, because anyway this is a 0 because we shift any number. And when we've done 5 iteration, we've built that number by shifting. So let's see if it's true. So we are no longer printing those things. So we need to do something else. So we no longer want the else print zeros, because we are no longer printing things. So we remove everything that we are printing. And okay, so when we are not in the if, okay, when we are not there, that means that we want to pad the last part with zeros, and this is exactly what will do that part. So we are not going to enter in that if statement, and so we are going to loop and put the zeros at the end. And now that we have the U5 car, maybe we want to print it, because if we don't print it, we are not going to see anything. So we print as an integer and U5 car. I hope I'm doing the right things, and maybe what can we do? A new line. Okay, so let's do a new line. So interesting. So we get 12, 25, 23, 16. And now it seems that we are having number. So 12, 25, and we see that those parts are wrong because we are not taking into account what we have after. But we have the 12 and we have the 15. And this is a first step, and we are almost done, I think, because we find the way to get those information. Something that we can do now before we do that with an array, and I hope I'm really doing the things correctly. So one moment, so we have the source here. Okay, so it seems the right moment before we instead of erasing the information that we get those 5 bits and putting them in an array, we are going to clear a little bit that part. We were getting those things with a character. So one moment. Okay. Okay, so this is the moment where I want to do something that looks like what is done in Core Lightning. Instead of a character, we are going to pass it a string, and instead of passing it the bit here, what we need to pass it, because we pass now, we pass directly the string, and we need the correct index which we have here. So we are just going to pass e plus I plus b that we have here. So let's remove this. We remove this because this is now some noise. So we want to change something here. We are going to change that, but let's take that string. So instead of the C character that we have here, we are going to use that string. The I plus b that we have here is in fact the bit that we are passing, and so we want to pass something like that. Get bit, we pass I plus b. Okay, so we have almost something clean here. No, this is not I plus b, sorry. So the first element now is not the character, it is the source string, and we want to do the modulo 8. So we pass the byte, so the modulo 8, which is instead of byte. No, this is bytes modulo 8, and we want that like this. And normally it's right, but we never know. So now it should be here what we have. We pass the string, and we pass where we are in the index of the overall bits that we have, and to get the right characters, we divide by 8 as we were doing before, and to get the right shift in that character of 8 bits, we get the modulo of the bit. And I hope I did the replacement correctly. We save, and source undeclared, where it is undeclared, blah blah blah. Okay, so let's go back here. Return source. Okay, I put string. This is not string that I wanted to put. Oh, now, okay, so this was an error. And now this is what we get. So cool. We are almost done with that things. Sorry, so I'm thinking while I'm doing it, even if I did it before and I've seen and I'm mimicking the code from big32 underscore utils. But anyway, this is what we get. And now maybe we have two last things that we can do. Is here instead of writing that overriding that information, we're going to put it in the right array. So we no longer use UK. Let's call it U5 data. So this is the array that we are going to construct. And I think that we can do that. This is a moment where we use the TAL library to allocate that array. First, that array has no length, so we use this is how it should then. So we can look at how it is defined. So allocate an array of object. We pass it null or a TAL parent to the allocation, the type to allocate, and the number we want. And the basic example with int will be an array of int will be this one. So we go back null, and I'm using that library because this is how dynamic allocation is done in Core Lightning. So what we want is to have the tools to understand the implementation of Core Lightning, maybe do some changes or fixes or anything that we might want to do. So an array of U5, length 0, and what we are going to do is that instead of putting U5 char to 0, this will be the first, the E, the first one that we are, no. I was going to tell something wrong, but I stopped before, so this is a good thing. Now, okay. We also need size t, maybe it's not size t, but anyway, we use that. So U5 data, the length, and the length is 0 at the beginning. And what we want to do, okay, so now I get what I want to do. So at length 0, so we want to set the first bit. So this is what we were doing with that character. So we set it to edit that way. Yes, this is that, but we see that now we try to put something in an array of a size 0 that we have here. So this is not that size. So what we need to do before doing something is to use tal resize, and we can resize the array U5 data. So we resize it, and how big do we want it? We want it to be the current length of the data plus 1. So yeah, this is what we want to do. We do this like that because if after the idea is really that when we go and look at the source code of Encode Lightning, we see almost the same thing, and this is done like that because in our case we know where U5 data, that array, we say that it's null. It's an array with nothing at the beginning, and we are going to build to make it bigger, and we make it bigger, and we put those 5 bits of information in each cells of the array. What happened in Core Lightning is that that function that is responsible to do the calculation that we do right now takes an array of U5 data that has already do some work. So basically, it has already the information, for instance, of the previous tagged part of the data part of the Bolt 11 invoice. So if we add the description, we are just taking that array and we add the description encoded, transformed in U5 bytes. So now the length is 0, but the system is the same. So we increment from 1. We set it to 0. Now we need to do the shifting, and this is what we do. So up. We do the bits that we get from the bytes of 8 bits now are placed in the array. And as we do that, we need to also update the length. So U5 plus at the end. So we do that. When do we do that? Yes, we do that each time we've done something with 5 bits. That means that we need to move position in the array U5 data. And so what we need to do is to increment the length, and then once we increment in the length, what we can do is we increment the size of the array with a new element, and we get continue to do that. And as we've seen before, in that part we also put padding. So when we are there, now we would like to print something to see that we've done something correct. So what can we do? So we know that there are 4 elements. So no, but we are going to do that like that. So I don't know if are we no, we want to go outside of that main loop. Okay, so we can use I 0, and now we are going to loop until, and we use tal count functions that give us the number of elements in the array allocated with tal, and we can take the U5 data. We do I++, and now we should be able, if we've done those things the right way, new line I, and we want U5 data. Okay, so this is the data, and we want that number. Okay, so we compile and show the result in the echo area, and we get the same thing that we have before, 12, 25, 23, 16. So, what we've just done, okay, so really what we've just done, we've done the conversion for that we see here. For the first, if we were to take only the first one and to do all that conversion, what we've done is to pass from this to something like that, with some changing the here, because we don't have those other characters. Okay, it's a video a bit long, but anyway, I want to go further and to end and to see exactly that one. We want that. Okay, maybe it's not that it should maybe take less time, but anyway, as we are here now, we can continue. What can we do? Okay, so maybe now it's time to, where is the source? So we have the source, we pass it here, and we constrict a data. Okay, so maybe we can fill that blank here with what we've seen. So this is a function that we call U5 to U8 to U5. And we get an array of U5, the array that we are constructing, U5 data that we have in the main function. It takes a source, and the source right now is FO for foo, but it's not foo, it's FO, and the number on bits is 2 times 8, which is 16. So let's abstract that in that function, and this is more or less what is done in Core Lightning, in the sense that they use, if I remember well, they don't use const 8 but U8 but void, and really I don't know why I use that, but I'm not skilled enough in C to see why this is important to do that thing with void. And we are returning an array of U5, and what is done is that in the first argument is the array that is modified in place. But we continue. It's not we won't go till that point, but at the end we look at big32 util, and this will be cool. So we abstract that, we put it here. We need at some point to return something, so we want to return U5 the data. So this is what we return, and this should work with no changes. The 16, we are going to change this for a number of bits after, but so far when I do changes like that, okay, yes, we are missing those declaration. This should be okay because we pass the source. Okay, so we have that. Okay, so we get a U5, a pointer on U5. data to see that we are not we apply that to the source string that we have. We pass this 16, which is the number of bits of that string. This is no longer U5 data, but only data, and we should have something that work. Sorry, what up? Maybe we should do something like that. So I'm not. It's new for me to use the TAL library, so I'm not sure exactly if I'm doing the things right or wrong. So please, if I'm doing it completely wrong, tell me, and I will correct and learn. But I think that we've allocated the data in in that function with TAL, and now we free that data with TAL free. And maybe we can just try that. So I undeclare, okay. So this is in the main. Okay, we compile and run, and within the echo area that we get what we wanted to get. So this is getting, we are almost at the end of what we wanted to do. Maybe we can do something a bit different, is that n bits here. So we need to replace those 16 by the number of bits that bits. So this should continue to work. So we compile and we see the result in the echo area. It continue to work, and now maybe we will change that to foo. Like that, and we can it's not longer 16 but 24. We evaluate, and now we go to 23, 22, and it's going to be better. So we see we have the 23, 22, so we are going to further from what we want to do. And okay, let's use directly foo bar. So we are ending. So 56. Normally we will have all we want to have. So this is not bad, but let's do something like that. So we do a precision of 2. So they are put the way we want. We go in the terminal, and maybe I'm going a little fast right now. It changed. I want the new line at the end. We compile run. Let's go back here. We run, we get those results, and if we look at the note, maybe we can put them side by side, and I think that we are good. So we have 12, 15, 23 on the left, on the right. So we have those 1, 8, 3, 2. So this is exactly what we wanted to do. And maybe the last thing that we can do, no, it's not that things, but because we want, remember in note, so we want this from one string to the other on the right with the beg32 car set, and this is why we've taken that array that add the beg32 character. So if we give here the q 0, this will be a p, 1, this will 0 will be a q, p will be a p, sorry, 0 is q, 1 is p, 2 is z, so till the end of that string. So now we can use that one, and we will do something like that, at that point an arrow like that, and we want %character, we want a character. No, this is not, see, yes, we want a data, but this is beg32 car set at the index data, the number I, and we should have something cool. So we have that, so we compile and we run. As we don't see everything in the echo area, we will go back to the terminal, and maybe we run beg32, and we get exactly what we wanted to do. Okay, so pretty cool, no? It took us a little bit of time to do all that session, but I think it's an interesting one. Tell me if you find it interesting, but to me this is really cool to see that part in action, because this is something that we can say, I don't know, making computers do what we want them to do requires to pay attention to the details. So I think that today we got through some of the details of the encoding of Bolt 11 invoices. That is I found interesting to see at least once, and to go and to look at, because really the goal, so this is the Lightning repository, and we go to beg32, is that right now with what we did today, that files should be easier to look at and to understand. So we see we did those things at the top, and what we were writing more or less is a beg32 push bits, and we see that we return an array of U5, and here the modify implies that array that is written at the end. So I hope, so we'll go back to our note. I hope this is a useful session, and I will see you in the next session. Have a good day.